one of the interventions, medical interventions that we've already talked about in class when we're dealing with the various types of diseases is antibiotics. Antibiotics in general, and traditionally, attack prokaryotes. Prokaryotes have different forms, and we've discussed this in class as well already. Prokaryotes, remember, means there's no nucleus. The cells have no nucleus. They have a plasma membrane, a single bilayer on the outside of the cell. They have a cell wall. The cell wall is not made of cellulose like in plants. It's made of something else, a different type of sugar. The cell wall surrounds the cell and allows the bacterial cell to survive changes in concentration in the solution that they live in. This antibiotic, this medical intervention, first derived from a fungus, another type of life on Earth that we've discussed, a eukaryote. That's a cell type that does have a nucleus. So pro means before. Pro means before. It does not, before nucleus. Eukaryotes have a nucleus. These fungi produce antibiotics to kill bacteria. And what they do is these antibiotics destroy the cell walls. And by destroying the cell walls, the bacteria can't live in an environment and keep homeostasis. And so they die. Homeostasis means keep balance. They cannot keep balance. They can't keep things stable. So the cells die. And we've been able to discover many different kinds of antibiotics from many different fungi. And we've even been able to adapt them and the antibiotics and change them, increase their efficacy, their ability to, how well they work by making these chemical changes to the antibiotics. But nature evolves. Evolution is a fact of life. Bacteria did not, in the history of life on Earth, did not just get destroyed by these antibiotics. They're still around. And what happens when these bacteria are exposed to an antibiotic, in this case we'll represent the antibiotic by these X's. Originally made by fungi, but now made by humans. We should discuss what's inside this bacterial cell. There is a DNA molecule that we have yet to discuss, a circular DNA molecule. Bacterial DNA is circular, and they have this smaller nucleic acid material, smaller DNA molecules that are called plasmids. Plasmids are small. They have unique information that bacterial cells can give to another bacterial cell. So bacteria don't have sex the way eukaryotes do. They're asexual. they do something called binary fission. They go from one cell to two, and from two cells to four. Fission means split, and binary means two. So they split into two continuously. Everything inside is duplicated. There's no nucleus, but they do have DNA. And somewhere, again, I wish we would have had time to discuss it before I got sick. I had to leave on Friday because I didn't want to get you guys sick. But these DNA molecules on them have these things called, these small regions called genes that produce, that give the ability, that produce proteins that give the ability for a bacteria to do something. They're functional. So the proteins that we've been discussing, because of the various amino acids that the gene codes for, produces a protein that allows the bacteria to resist the antibiotic. The antibiotic then does not destroy the cell wall, and the bacteria survives. This gene, obviously the original bacteria did not have that gene. That gene didn't even exist. What happened was a mistake, an error. This mistake or error you would know as a mutation. Most errors, or mutations occur and have no impact on the bacteria or on the function of life. Most errors occur and they just accumulate. But once in a while, the mistakes that happen change something. The change could be bad, and often is, or it could be good. So that's the background that you're looking at. You're looking at these antibiotics that destroy the bacteria, that kill the bacteria. You have these cells that do binary fission, so they duplicate by splitting. They have these genes that are on these circular chromosomes that, because you're splitting and making copy after copy after copy, you're often, mistakes accrue. And every once in a while, one of these copies is going to have a mistake. And that mistake could be the key to that bacteria not dying, not being affected by the antibiotic. What happens is that gene, in this case the red, that gene, that new mutation, makes that cell slightly resistant. Meaning that it takes a higher concentration of the antibiotics to kill that cell than it would these others. And even though antibiotics, when given to humans, don't really impact our cells that much because they're attacking the cell walls, at high concentrations, anything can be deadly. All things. The difference between poison and medicine is just dose. It's just the concentration. So when you're given antibiotics, the doctor looks at your weight, how much blood you have, your age, how you metabolize the antibiotic, perhaps kidney function, liver function, or what have you. and they give you a dose that's going to kill the antibiotic but not do damage to you. So there's a limit to how much antibiotic you can actually take in your body safely. At a certain point, at a certain concentration, a lot of these bacteria are going to die. And it's going to take time for them to get that concentration into their bodies and for that cell wall to break down. Often it's, antibiotics are given for 5 to 10 days, depending on the type of bacteria, the antibiotic, and how it functions. So over those 5 to 10 day period, over that 5 to 10 day period of dosing, you have these cells dying off one at a time. That one's dead. That one's gone. That one's gone. This one goes. This one goes. The concentration antibiotic is strong. It's large enough to kill all of them if you give it enough time. After 2 to 3 days, what happens is you start to feel better, and some people stop taking the antibiotic because they feel better, so why should they take it? Well, what happens is that one bacteria that had that gene that made it slightly resistant now has a lower dose of that antibiotic because you're not taking it. All the rest of the bacteria are dead, but now this one cell with that gene that made it resistant is able to do binary fission and makes copies of itself. And you get sick again days later, except now all the bacteria in that population, all the bacteria have that resistant gene. So that antibiotic no longer works. Now this is made worse by our factory farming techniques because we expose chickens and cows to antibiotics to keep them healthy. But we also what we're doing is we're allowing bacteria to be exposed to the antibiotic that could develop resistance to that antibiotic and make that antibiotic not useful for controlling the population of bacteria. And of course, if these bacteria end up reproducing in high quantities in your blood or in your tissues, you get really sick and you can die. This is only one level of protection your body has. Your body has a natural immune system as well. But for antibiotics to help you fight off disease, specifically bacterial diseases, the antibiotics cannot be overused. If you have bacterial resistance, if you have an antibiotic that works, you have to restrict in your, let me rephrase that. You have a large number of antibiotics that have become not useful because there are some strains of bacteria that are resistant to that antibiotic, and many of our antibiotics. And so there are some strains, these superbugs, which we have a lab. Once we get the lab, our supplies in, we'll do the lab, and I think you'll understand better when we do the lab. We have these superbugs. And by the way, in the lab, we will actually see this happen. We will make the bacterial strain that is resistant to an antibiotic. We won't let it loose. We will kill the bacteria. But you'll see how this occurs in real time. These superbugs have developed, these bacteria have developed that are resistant to all the antibiotics we have. Or most of the antibiotics we have. We might have one or two special antibiotics, newer ones that haven't been overused. Some people might call them powerful. realistically, they're probably less powerful and just more underused. And because they're underused, the populations of bacteria have not been exposed to these antibiotics. So the resistance gene has not been developed by the population. So it's up to health officials to restrict the use of these antibiotics, to make sure that we only use them when absolutely necessary. And the reason is that if we overuse them like we have the others, we won't have anything to fight off disease. And to give you the scale of the problem, to help you understand the scale of the problem, before antibiotics, the most common way people died was a bacterial infection. It wasn't a virus really that we were super worried about. It was bacteria. If you got shot or cut, it became an issue. Often the solution to an infection was removal, amputation of a limb. We had toothaches killing people. A tooth infection killed people. In fact, early doctors were often dentists. It was that serious. It was antibiotics that changed the world and allowed the world that you've grown up in, this cocooned world that where you feel like you have a hospital place to go to help you if you get sick, that didn't exist in my grandfather's time. When my grandfather was a young man, there were no antibiotics. It was during World War II when he served in World War II, was then they developed the first antibiotic, penicillin. So when you're looking at this world that you've grown up in, these bacteria, without any antibiotics, we could easily start entering a new world where we have to really concern ourselves with bacterial infections and how we deal with bacterial infections at a large scale. And we might see a lot of people dying from preventable disease. Again, these are antibiotics. Do not confuse them with vaccines. Vaccines are a different medical intervention that we have discussed, and we will discuss it again once I'm back in class.